let's see. Okay, so what we're going to talk about today are some more components of the standard template library. The first thing we're going to talk about is something called an iterator. Let's advance this. Okay, so last tutorial, just to recap, we learned about C++ templates. We can write function templates, we can write class templates, and it's a way for a strongly typed language, like C++, strongly typed, meaning everything's got a type. That makes your code more efficient. It also lets the compiler do more error checking. Well, templates let us create code that'll work for multiple types by writing a recipe. And we talked about writing templates is a bit more tricky, but using templates is pretty easy. And there's a really powerful library that is part of C++ called the Standard Template Library, or STL. And the particularly useful part of this library, lots of useful things, but the most important part of the containers library. And we learned how one of the data containers in there, vector, works last week. So we're going to learn some more this week. So the first thing we're going to learn about is something called an iterator. And we're going to learn what is it, what can we do with it. Iterators basically are a generalization of a pointer. They behave like a pointer, but they're actually a class. But you can think about the way you use them as the way they mirror a pointer. And often their implementation actually has a pointer inside of it. But basically, if you think, what would I do with a pointer? That's pretty much what you would do with an iterator. We're going to talk about why these exist. They basically exist because you can't really use the container classes without iterators. So the generalization of pointers. And then we're going to talk about one of the container classes, list, so our second container class, which you really need iterators to work with. And we'll talk about how list is different from vector, the first container class we learned. That's kind of the first half of this tutorial, then we'll talk about some other things in the second half. Okay, so first thing I want to talk about iterator. So I already told you some of this. It's used to identify an element in a container, and it is a generalization, an abstraction of a pointer. It behaves like a pointer. It allows us to access an element in the container. It allows us to move between elements. So again, like a pointer, we could point at element 1, we could point at element 20. And C++ is a language for speed. So the standard template library tends to limit you to efficient operations. Okay, so what do I mean by that? You're going to see that there are a few different kinds of iterators in the standard template library, depending on what kind of container you're using. So they're a little different for vectors than for lists. They have different capabilities. And the rule that the STL uses is make the operations that an iterator supports efficient. If it would be theoretically possible to make it support this operation, but it would be really slow and no one should use it, then just don't do it, so you'll get a compiler error. And that's actually doing you a favor. They're making it more difficult to write slow code, saying if you don't know what you're doing, using the wrong kind of container, the wrong kind of iterator, they just don't compile it, rather than compiling really slow code. And you'll see what that means in more detail in a little while. Throughout some of these slides, there are little references if you want to go learn more. So the standard template library is huge. Nobody memorizes the whole thing. So there are a couple of references that are referred to in the slides that you can click on to go look stuff up. And you're going to do that throughout this project, throughout your career. Okay, so why do we have iterators? I told you they're like pointers. We already used vector, and we already did some useful things with vector where we just used this subscript operator, the square bracket operator. So we can use array or vector of index to get at different elements. So why do we even need iterators? Well, for a vector, you don't actually need them so much because you do have this ability to just use indices with the square bracket operator. So if all we had was vectors, then maybe we wouldn't have iterators. We'd just use indices. But that's not the only container. There are other containers. And those other containers, like list, do not have this square bracket operator. It doesn't exist. So we need an alternative. Why do they not have the square bracket operator? Because the square bracket operator implies random access. I can ask for entry 2, or I can ask for entry 2 million, and then both of those things, I can get them back quickly in order 1. So if I can't do that with a list, and you can't, the operator doesn't exist. So we need an alternative to be able to refer to elements of containers like lists. Okay, so in STL, some containers like vector have this subscript operator, but some don't, like list. But all of the containers have iterators, this generalization of a pointer. Now, iterators behave like pointers, but they're really classes. So when you want to use an iterator to refer to an element in some container, you have to get the right kind of iterator, like the right kind of class. So, and their type looks kind of long. I'll show you a way later in this, in these slides how to shorten this. But to start with, we're going to use the full kind of long way of declaring their type. So let's say I have a vector of integers, and I need to make an iterator so I can go through it. So this I would declare a variable of this type. Basically, it says in the standard library, there is a class, a templated class called vector. I am using a vector of integers, so I want that recipe applied to integers. And inside that class, there's actually another class that is the iterator to go with it. So I want the iterator that goes with that. So that's the whole type for an iterator that would work with the vector of integers. If I wanted a vector of floating point numbers, I would change my iterator declaration a little, right? To the iterator for a vector of floats. And if I had a list, it would change a little bit as well. So I'd say in the standard library, list of integers, well, I want the iterator that goes with the list of integers. So the type declarations for these are a little bit long, but you got to get the right kind of iterator. Okay, so let's talk about standard vector a little bit, because that's the one container class you've already learned about. So you already know that, just to review, that it has this subscript operator, and we can use that to read elements. We can also use it to modify elements. Here's a question to see if you were paying attention last week. Can I use that square bracket operator to create elements? What do you think? No, do not do that. Bad, okay? But I can use the pushback operator to create elements at the end. And I can ask, how many elements do you have? Size. All of those things are fast, order 1. Okay, so now I'm going to teach you a couple of new member functions that are useful for iteration, for going through all containers, but we'll use vector as our first example. So there's a member function called begin, and it returns an iterator that points to the first element in the container. So in this case, a vector. And there's a member function called end that returns an iterator that is just past the end of the container. Okay, so it doesn't actually point at part of the container, it tells you you've gone too far. So it's kind of like a vector goes from 0. If you have a vector of 10 elements, you can access from 0 to 9, but you shouldn't access 10. 10 is like too far. That's what end is, okay? End is not the last valid element, it's just past that. When you get to the end, stop. Does that make sense? Okay, so this just kind of shows that. So if I have a vector, maybe I called it my vector, and its size is n elements. And I probably should I shouldn't make this look like I'm doing an assignment. I'm going to change this slide to say it's equal to, okay? So it is n. The begin will point at the first element, the one that's at index 0, and end points past the last element, okay? So we should never try to actually access something at the end. We just use it to tell when we've gone too far. Does that make sense? Okay, so you don't know much about iterators. You only know probably what I've just told you. But despite that, I want you to use your logical powers, that they behave like pointers, okay? So I'm gonna get you to, with another person at your table, try to fill in this little table of what's gonna work. So I've got a vector of integers that I've declared here. The name of the variable is numbers. And in C++, we can initialize data structures with this curly bracket notation. So this just means that vector has 4 elements in it, index 0 to index 3, and these are the numbers that each one of those elements is set to. So that's what I've got to begin with. And then we've got 9 lines of code here. So I want you to look at each of these lines of code, and knowing that an iterator behaves like a pointer, it is a generalization of that, try to figure out which of these lines would compile, okay? So compiling means they do something that is reasonable. If it's completely unreasonable, then STL is probably, like C++ is probably not, well, it will not allow it to compile, right? If it doesn't make any sense, generally C++ says, I won't compile it because you want to know that right away. So with a partner, go through, I'll give you a minute, think about which of these you think would work. Also think, I was also going to ask you, what do you think this line of code would do? And again, think of it like pointers. So this is a generalization of a pointer. If you and your partner get this correct, you each get a tasty chocolate bar, okay? So hopefully that motivates you. So when you think, I'll give you a minute, and then some team that is happy to try, we'll let you take a shot at it. Okay, anybody ready to go? Okay, who has not tried one of these things too? You guys tried it, you tried last week, right? I'll come back to you, but I'm gonna give another team a chance to do it if you've never taken a shot at one of these. Anybody who has not taken a shot at one of these challenges, want to try? Not too intimidated. This is like the restaurant. So, they're like, oh, this guy's is so good, we can't compete with this. So, who wants to take a shot at this? Is it lack of bribery, or is it fear of being wrong? It's weird. It's really weird. Okay. Do you want to take a shot at it? Sure. Okay, go for it. Yes. Well, no, you gotta go slower. Okay, I'm slowing you down. First line. Okay, so first line is this. Declares an iterator, right? Iterator of vector of integers. Is that the right kind of iterator? Yeah, it's the right kind of iterator. Good. Calls it it, so it's named the variable, and it sets it equal to numbers dot begin. Numbers is my vector. What do you think? It's going to work? Yeah. What does it do? It will work. So, right, points to the very first thing. Okay, so begin's going to point. Well, which one of these is? Maybe this is too obvious, right? This points at that. Okay, so that's where my it is to start with. Maybe I'll write down. This is what it is. It's pointing at that. Oops, my writing's messy on this thing. Okay, so that's going to work. What about the second line? It equals 5. It's going to work? Okay, does not work. You're correct. Why did it's kind of nonsense, right? So let me ask you one thing. I said this is like pointers. In C++, could I actually set a pointer equal to 5? Yeah, you can with typecasts. By itself, it's going to say it doesn't make sense. With enough casting, it'll accept it. And the reason C++ allows that is it inherits from C. And for very low level code, like when you're writing in 243, you actually, with a pointer, might do this. You might actually say, I know that memory address 5 is what I want. You can only do this with really low level programming. So for point, this is a case where an iterator is a little bit different than a pointer. For a pointer with a cast, you could do this. Iterators, they always have to point within a container. They can't be used to just point at arbitrary memory addresses, right? Like they behave like pointers, but they're not exactly pointers. So you're right, that makes no sense. Cannot do that. So far, so good. What about this? IT++. Yeah, so what does it do? Right, so did you guys study pointer arithmetic in 244? You know what I mean by that? Yeah, so when I with a pointer, if I do this, it basically knows how big every entry is in say, an array, and it would go to the next entry. And that's exactly what this does for this vector. It goes to the next entry. So after this, my IT is no longer pointing here. It's now going to point at 2. Okay, what about case 4? Is it going to work? It's going to work. It's going to do the exact opposite. Okay, so IT was pointing at 2. Now it's pointing back at 1. Okay, what about this int x equals star it? Is it going to work? What does it do? It assigns x to right, assigns 1 to x. So it is pointing at an entry that has value 1. This says get the value I point at, set x equal to that. So yeah, x will become 5. It's going to work fine. What about it not equal to numbers.in? Is that going to work? Yeah. This is actually how we use iterators for iteration. We have to be able to compare them to other iterators. And the end is a special value that we should think of as being past the end. okay, like past the last valid entry. And this is going to return true. The iterator is not equal to n. Does that make sense? It's actually pointing at a valid entry, not equal to n. What about IT less than numbers on it? So you're guessing no, and this one is actually a weird one. Okay, so for this one you go, well, with a pointer I could do that, but does it make sense with an iterator? So this is where different kinds of iterators behave differently. Vectors have a fairly powerful iterator that is called a random access iterator, because we actually have an ordering of things in a vector. We know this is index 0, index 1, etc. So we actually can compare, is this iterator less than that? So for a vector, this will actually work. And it will return true if this iterator is before the end. But you're right to be worried about this one, because for some other things, like a list, this would not work. Okay? It has to be basically a powerful iterator called a random access iterator, which vector has. So I'm going to give that one to you. If you're right to be cautious, but that one will work for a vector. What about this? And what does it do? Right, so this one will be gone, and we'll now have the number 27. And what about this last one? IT equals numbers begin plus 2. You can think back to the conversation we just had. Yeah, that's exactly right. So for a vector, which is a class of iterator called random access, a powerful iterator, it will work, and it will actually move it forward 2 elements. Okay, so our iterator would go to there. So well done. So you guys can come up and help yourselves to chocolate us. So, or you can do it in the break if you prefer, whatever you guys like. Okay. So let's look at a quick bit of code that actually uses an iterator. That was all kind of little snippets of code. So we saw last week that we can loop through a vector and do things using indices. Okay, so here's my vector. It's got 4 elements in it. And I can loop through. Size t, by the way, is have you guys ever seen size t? Do you know what type size t is? Does anybody know what type size t? Size t basically just means unsigned integer. Okay, so maybe I should have just written int, but I could have written int here, could have written unsigned int. Size t is basically an unsigned integer that can be used for iteration. So just think of it as int. Maybe I should change it to int to avoid confusion if you've never seen this before. Because it is really a synonym for an unsigned int. Okay, so I can go through this from index 0 up to, but not including size, and I can just use my square bracket operator to get every entry and print it out. You did that last week. Okay, I can also write that exact same code using iterators. And basically, I have to declare the right kind of iterator. So I need an iterator for a vector of integers. I call it IT in this case. I initialize it to point at the first element, because numbers is my vector. So call the member function begin, make the iterator point to the beginning. I keep going as long as I'm not at the end. So that's the equivalent of that less than numbers.size check. That's my end check. And every time through, I increment the iterator. I'm using pre-increment here. If I did post-increment, it's the same. So somebody in another class asked me, what if I did IT++? It's fine. Whichever way you like to write it that way. Okay, and every time through the loop, I'm going to dereference the iterator to get the elements at that point, and I'm going to print it out. Okay, it'll generate the exact same output as the loop above. It'll be the same speed. So these both are going to compile to basically the same machine code and run at the same speed, generate the same output. Which one do you like better? Okay, so we learned how to write this with indices last week. Now I showed you how to write it with iterators. Do you have a preference of which of these you would write? How many people like the iterator version? Nobody likes the iterator. How many people like the index version? Okay, and I think the rest of you maybe don't like printing. Okay, so I would prefer to just have this vector remain anonymous. Yeah, I actually like the index version too. So when you look at this, there's nothing wrong with the iterators, but I find the index version easier to read. So that's actually what I would write as well. So I'm teaching you iterators, it doesn't mean you need to use them as much as you possibly can. The reason to understand iterators, though, is that there are things where containers where you have to use them. Okay, so a vector, often you don't have to use them, but there are member functions and containers that you must use iterators. So in those cases, you have to. But when you can use indices like a vector, it's fine. I actually prefer to use indices when I can too. Okay, so that said, though, I'm going to get you to write a bit of code using iterators. So this is basically the function that we wrote last week, where we're going to extract all the negatives from a vector. So we're passing a vector in, and called integers, and we're making a vector called negatives, which we're going to return. And I want you to use iterators to go through this integers vector, right, the one that's passed in, and add all the elements that are negative into the negatives vector. So this isn't going to be very much code. It's going to be a little bit. You are going to use the pushback function that you used last week. Okay, you still need that. Good way to create elements. And you could write this whole code with just indices, but I'm going to get you to write it with iterators instead, so you get a little practice with that. So go to the online IDE. So it's the same one as last week, codeboard.io projects, but this project is 208499. So do it by yourself, do it with a partner at your table. I'll give you 4 minutes. Try to write the code in exercise.h. Compile it, run it, runs a couple of test cases that we've written. You can tell whether or not it works. Okay, so take 4 minutes and take a shot at this just to gain some expertise in writing code with iterators. Sure.
If I change the container with the iterator, be messed up.
What do you mean by that?
Like, let's say I have a list and I have an iterator pointing to the middle of it, that add another element.
I see, okay. Like you insert something?
Yeah, or like for a set or something like that.
Yeah, so the iterators can be messed up sometimes when you add things. I'm going to show you an example in a minute where we do that, and we have to actually be careful with the iterators. So not this one, because this one you're just reading something that you're not changing, in which case the iterators are nice and very easy to think about.
Yeah.
You're right, when you're changing the container using iterators, you have to be careful, because your iterator might not be pointing at anything reasonable. The library has a way to handle that, but I'll show you.
Oh, I mean, like, let's not like changing it using the iterator. Like, if I just had an iterator pointing at something,
oh, and then you would change
I'm
something?
storing it, and then I change something through the iterator, like dot pushback or something.
So pushback doesn't take an iterator, okay? But you're right,
yeah.
But pushback can change the container.
Yeah.
Yes, there are certain operations that can invalidate iterators, okay? And pushback actually is one of them, so you have to be careful.
Okay.
The reference that I've listed, the C++ reference, tells you for every member function if it invalidates iterators. Yeah, so it's not a secret. It's basically, so a good practice is like you set the iterator up, use it right away, and then just assume and don't use it again without setting it up. And then you don't have to worry about it too much.
Okay.
If you have this iterator hanging around for a little while, then you do need to check, did I do anything that could have invalidated it? Because there are some things that can invalidate it.
Okay.
But they're all written down. They're very clearly specified for every every container class and every member function. Does it invalidate iterators or not? So the reason pushback, for example, invalidates iterators, well, can you think of why? Because sometimes it copies. Yeah, if it didn't copy, it wouldn't invalidate, but once in a while it copies. And the iterator class, you can guess probably that inside of it, for a vector, it actually has a pointer. Okay, that's how it actually keeps track of where it is. And when you call pushback, the vector updates itself. It knows it's been reallocated. But if you just had an iterator lying around, nothing updates it. So the solution is don't have an iterator lying around while you're calling pushback. Like, well, it's okay to have the type, but just do not assume that iterator is pointing at anything reasonable after you do a pushback. You have to make it point to the container again. Okay. Does that make sense? Yeah. So it's a good question. You actually have to be careful about it.
So it's less powerful than I thought it would be for some reason.
is not like auto updating or something. Like, there's no dynamic links of like this thing gets, because that would just be a mess. And again, C++ is also designed to be fast. So it's not trying to like, I'll make code that kind of does complicated stuff that you might or might not want, because that's not the purpose of the language. It's like, I will sometimes do complicated stuff, but only if it's fast and you ask for it. Does that make sense?
Yeah, thank you.
You're welcome. Yeah. So you got it? Okay. Okay, so it looks like most people were able to get it going. Everybody feel good about the iterators now? Well, let me show you my solution, which yours probably looks an awful lot like this. So I have this complicated declaration, right? In the standard library, I want the iterator that goes with a vector of integers. That's what that means. I'm going to call it it, make it point at the beginning of my vector. I want you to go through until it's pointing at the end. And every time through, I want you to increment it. Okay, so that's pretty standard iteration over a container with the vector, or with an iterator. And for every element in the vector, I'll just check, okay, dereference the iterator, so check the value I'm pointing at. If it's negative, I'm going to put it in my negatives vector using the pushback member function, okay? And I don't want to put the iterator in my negatives. I want to put what the iterator points to, okay? So I got the star IT. Okay, if you did that, you pass the test case. Okay, so that was taking all the negatives out, putting them in a new vector. Now I want to do something to actually show, this one actually I do need iterators for. So now I want to remove the negatives. Here's a new function. I pass in my vector of integers again. Okay, I pass it in by reference, which means I can change it, and the changes will affect the caller. I'm going to iterate through again, so I declare my proper type of iterator. I make it point at the beginning. I keep going until I'm at the end. So that's all normal. But I don't actually increment it in the for loop, or not in the header of the for loop. Okay, so that looks a little weird. Why do I do that? Well, here's the work of the for loop. If what the iterator is pointing to is negative, then I want to remove it. Okay, that's my goal in this function, get rid of the negatives. And there is a member function called erase. So you don't expect you to know this or memorize it. You go to the standard library documentation, and it'll tell you, yeah, there's this erase function. So that's what I want. I want to get rid of this thing. It takes an iterator, and it destroys what that iterator points to. Okay, so that means if it has a destructor, it calls the destructor. For an integer, there's no destructor, so we don't care. We just call erase, it's going to do the right thing. And in a vector, destroying an element also means you got to get rid of the hole, right? Like a vector does not have holes in it. That's what makes it fast. So the vector, if it had 10 elements, after I call this, it's got 9 elements. And if this was pointing at the fourth element is gone, okay? Everybody got shifted over one, there are only 9 elements now. So that's good. This does exactly what I want. But there's a tricky thing here. I was pointing at element 4, say, and I just said erase it. So now what am I pointing at? Like the thing that I'm pointing at, I just told you to destroy. So my iterator is pointing at something that no longer exists. That's a problem. So what the standard library does is when you call erase, it returns a new iterator. So it takes an iterator saying, what do I want to destroy? And it returns a new iterator. So if you're looping through something, you can keep going. The iterator it returns points to the next thing after what you just destroyed. Does that make sense? So if it's negative, I destroy it, and the erase function returns an iterator to the next thing. If it wasn't negative, then I should just skip over it, which means I just increment. So this if and this else together will properly advance my iterator, but I have to do it in a little more, it's a little more code to advance the iterator than when I was just looping through and printing things out. Now that I'm destroying things, I have kind of 2 cases. If I destroyed it, I should use the new iterator. If I didn't destroy it, I could just skip over it with ++. Does that make sense? So you'll find that functions in the standard library that destroy things, that change things, they often will take an iterator. That's how they identify what to do. And they will then return an iterator because they just got rid of whatever you created. They got rid of what you were pointing at. You don't memorize all this, so I'm telling you so you're aware of it. The standard library documentation is very good. Go look at the erase function documentation. It tells you all of this. Okay, so you don't memorize it. Okay, so what does erase do? I already kind of told you this. So I'm going through this vector. I've already looked at a bunch of elements, right? So we'll call those the processed elements. My iterator is pointing at this number, and it happens to be negative. I wanted to destroy it. I call erase. I pass erase.iterator. Okay, now that entry's gone. So I get a new iterator. Here I call it ite2, that's returned from erase. And it points at the next unprocessed element, okay? So which is exactly where I wanted if I was walking through this whole thing in a for loop. Oops, actually, I already had that, okay. Make sense? Everybody with me? Okay. Okay, how does this perform? So erase on a vector is slow, okay? Why is it slow? Because vectors can't have holes in them. So when I destroyed this element, the vector code the vector erase member function had to copy over every single element after it, shift them all over by one. That's actually an order n operation, right? It had to go through every single one of them, and basically what was at index 5, it has to copy to index 4. What was at index 6, it has to copy to index 5, and so on. And if there's a million elements, it has to do that for a million of them. So that is an order n operation. So given that, what is the complexity of removed negatives? Shouldn't have shown you that. I don't know how fast you guys can read. Well, how about this? I'm going to give you a chocolate bar. If you read really fast, you'll get it anyway. Okay, you guys get a chance now. So I bypassed you last time. I feel a little guilty about it. What do you think? What's the complexity of removed negatives? It's n squared. Why? Right, so I've got a loop of n that goes through n times, and every one of them, if they're all negative, I'm going to call erase each time, and it's order n. Okay, so it's order n squared, so whatever is convenient, grab yourself a chocolate bar. So, okay, so this works, but my extract negatives functions is quite slow, because order n squared is not good. So this is where you start going, well, maybe I should use a different container class. So, and a container class that is a much better choice here is list. So the list container class in the standard library is a doubly linked list. This is what you guys built in 244. So everybody remember list? You with me? You remember it? It was beaten into you? Good, right? So the data is what you're actually trying to store, right? Maybe it's an integer, maybe it's a resistor, maybe it's a string. Every element has a next pointer to go forward and as a previous pointer to go backwards. And we have a head and we have a tail. When you work with lists, I'm showing you how it works. You don't directly access next, previous. You can't even directly access them. You work with it through the member functions. So I'm showing you how it works, but you don't need to know that level of detail. Okay, so the nice thing about list is if I call erase, so I have an iterator pointing at this element, I call erase, it gets deleted, and then this next pointer, the one before it gets updated, and this previous pointer, the one after it gets updated. That is an order one operation, right? I didn't do any looping, nothing. It was all constant time. So erase is very fast. There's another function called insert that puts a new element in right after an iterator. So that's also fast, okay? So what is the strength of list? It's really fast, it erases in the middle and inserts in the middle, whereas vector is slow. Does that make sense to everybody? Okay. Okay, so let's look at, this is kind of your menu on STL. You should be thinking about what are different container classes good at. So we think of the complexity, and the documentation on the STL gives the computational complexity of every member function. because again, C++ is intended for speed. So it tells you how fast is this. So begin and end, right? To get our iterators, they're both order 1 for vector and list. Pushback is fast, order 1 for both. Size is fast, order 1. It's obvious why it's fast in a vector. We saw that we store the size, so it's order 1 to return that. In a list, it's fast because we also store the size. If we had to go through the whole list counting things, it'd be order n. Turns out people call size often not the standard library. In recent versions, also just stores it. Okay, so now it's constant time. Square bracket operator, big strength of vector, it's order 1. It is not available in a list because you cannot make it efficient. If you tried to build it, it would be an order n operation. Doesn't really make sense, just will not compile. Erase and insert, very fast in a list, very slow order n in a vector. Okay, so that's the weakness of the vector. Okay, and then iterators. I told you there are different kinds of iterators. So we can get an iterator for a vector, we can get an iterator for a list. So the iterator type for a vector is called random access, and you already saw what it can do. It can go forward, it can go backward, and it can also actually just skip forward 5 elements or 1,000,000 elements, because they're all order 1. The iterator for a list is a bit weaker. It's called a bidirectional iterator. We can move it forward 1, we can move it backward 1, and that's efficient, right? It just looks at the next pointer or it looks at the previous pointer. We don't look at that, but inside the class, that's what it does. +5 or +1,000,000 cannot be efficiently implemented for a list, so it just won't compile. Okay, you try to do that, it won't work. And it's doing you a favor, because if you actually wanted to use that, the compiler is telling you that doesn't make a lot of sense, maybe you should think about vector. Does that make sense? Okay, so I guess I've been talking now about these iterator categories. So there are random access ones, which are like a vector, bidirectional ones, where list is an example. So we can do all these operations for a vector, we can do somewhat fewer for an iterator for lists, and there's an even weaker class called forward. Forward, basically, you can dereference the iterator, so you can look at what it points at, and you can move it forward, but you can't move it backwards, okay, so even weaker. There's another class in the STL called a forward list. A forward list is another kind of linked list. It has next pointers in it, but it doesn't have previous pointers. So you can go forward, but you can never go backwards. Why does that exist? Well, if you know you're only going to go forwards, it's a little bit more efficient, right? There's a little less overhead because we don't even store the previous pointers. You know, more commonly, you want to be able to go both ways, so people usually use the bidirectional version, but we also have the forward one only in case you want that. Okay. Any questions on that, or it all makes sense? The good news is if you try to do something that doesn't make sense or work, you just get a compiler error. So then you look at the documentation and you figure out, oh, that doesn't exist for that. Maybe I should use a different container class. Okay, so we wrote this extract negatives function, and it's order n squared, which is bad if n can get big. And we figured out that list, because it has a much faster erase operator, would be better. Okay, so here's another chocolate bar question. So anybody want to rewrite this with a list instead of a vector? Everybody wants to rewrite this with a list. Okay, so I'll give you a second to think about it. Okay, you, what do you do? How are you going to rewrite this with a list? Okay, so you're saying get rid, first thing, makes sense. You want to get rid of this vector, and you're going to use a list. What about this vector? It's going to be a list too? Okay, what about this? That was it. I only had 2 vectors, I think. So you're going to replace them with list. Anything else? Okay, let's see. That's it. Okay, so that, so well done. You get a chocolate bar whenever you feel like it. So it's one of the nice things about the STL. They make the library very consistent. It gives the same member functions with the same names for all of the containers. So you can, I just figured out that my teammate did a bad job, used the wrong data structure, and I changed the code. It made it way faster, and it was really easy, right? All I did was ask for a different data structure. So that's a nice thing that makes it easier to remember the standard library, easier to change things. Okay, so yeah, this should be much faster now. Now, If I was using the square bracket operator, something that vector has that list doesn't, then I'd get a compiler error, and I have to go fix that. So you can't always change from one container to another and everything just works, because you might lose some operations. But if all the operations that you're using exist for the new container, it'll just work with no changes. Okay, so let me show you one last little bit of syntactic sugar, a couple pieces of syntactic sugar. Recent versions of C++, and we're using recent versions in the lab, allow you to shorten your type declarations in many cases with a new keyword called auto, okay? So you saw those iterator type declarations kind of long. So they're okay to write, but they're a bit of a pain. So if the compiler can figure the type out from your code, you can use the auto type instead. The type does not change, so this doesn't mean it's Python. In Python, types can actually change, right? You never say what the type of variable is, and it actually can change as you assign different things to it. That does not happen in C++, and it's for efficiency reasons. And so it can check your code more at compilation time. So there's still just one type. It's just when the compiler can tell there's only one legal type that could possibly be used here, you can use the word auto, and then we'll just fill in the blanks rather than you typing it. Okay, so what that means is you can only use the auto keyword when you're immediately assigning a value to it, because that's how the compiler figures it out. So in this code, I'm declaring the iterator for vectors of integers, and I'm immediately assigning an iterator, right? The result of calling the begin function on my container numbers. So the only way this will compile is if the iterator I asked for matches the iterator that is returned from this function. So I can just use the word auto, because the compiler says it must be the type that this function returns, can't be anything else. So I can save some typing if I want. And this is very commonly done for iterators, because it's kind of tedious to write this long iterator, and it doesn't actually convey any real information, because you either get it right or you get it wrong. If you get it wrong, you get a compiler error. Does that make sense? On the other hand, if I did something like, I cannot do things like this, just write a line that says auto I, the end. What is I? I have no idea, right? Haven't assigned a value to it. There's no possible way for the compiler to figure out what do I want. This could be anything. So you can't do that. If you want another little bit of syntax that can be convenient, so you don't ever have to use this. So if you're like, I've had all the syntax I ever want, you can now just blank out for the next 30 seconds. C++ also has what's called a range-based for. So range-based for is intended to be used with the standard library containers. Okay, so here I made a vector of integers, called it numbers. And I can basically use this syntax if I want. I can say, I want to go through the whole container, numbers, the whole vector. Each iteration through, I want to call the item in that index, I want to process one item from the vector, okay? So this is going to loop through the whole vector. Every iteration, item is going to refer to the next element. So I could write this code and just print out item, and it'll print out the vector. It's no faster and no slower than writing it with indices or iterators. The compiler actually turns this back into essentially the same code you would have written with iterators or indices. Okay, so it's not anything magic. It's just people write the same code over and over again of, for it equals numbers.begin, it not equal to numbers.end, etc. That basically C++ has made a shorthand for it. And effectively behind the scenes is filling in the blanks for you. So if you like that shorthand, you can use it. If you don't like it, never use it. It doesn't really matter. Okay, and I'm not going to talk any more about that. Okay, and I'll give a quick demo, and then we'll take a break for a few minutes. Okay, this is. Can everybody see this? Is this big enough or not? Can you guys see the code? You can see it? Okay, good. Let me scroll down a little bit. Okay, this is a pretty simple program. It's the remove negatives program, basically. So what am I doing here? I'm declaring a vector of integers, and I'm saying I want to have 1,000,000 numbers in it. I go through and I insert a 1,000,000 random numbers in the vector, okay? Half of them are negative, half of them are positive. Other than that, I don't really care. They're random. And then I go through and I'm going to remove all the negatives. Okay, start at the beginning of it, keep going to the end, and basically do that erase function to get rid of all the negatives. And that's the end of the program, okay? Okay, so it's my remove negative function on a vector with 1,000,000 things in it. Okay, so when I go to, let's do a clean, I'm gonna time this. What build should I use? What build configuration? You say release, you're right. Okay, so don't time things that are not release, because you might get misleading results. Okay, so I use my handy time function. Okay, so it's erasing 1,000,000 negatives. Doesn't sound that complicated, right? Like we've written programs a lot more complicated than that, but it's still running. Okay, so it's taking a while. It's getting a little awkward, probably going, hey, when's the break? Okay, so it's done. It took 18.5 seconds. Okay, and remember, this is order n squared. We said vector was not a good choice for this. Okay, so let's look at the options we have. So this is the list version, and it's the exact same program, with the only change being that instead of a vector of integers, we're making a list of integers. Make 1,000,000 of them again, half are negative, half are positive. We're gonna go through, we're gonna remove all the negatives. Okay, so list, we said this would be order n if we used the list instead of order n squared. So it took 18.5 seconds with a vector. How long do you think it'll take with a list? Okay, whoever gets closest, I'll give you a chocolate bar. Okay, so 18.5 seconds for a vector. I'm gonna give you a hint, it'll be faster with a list, okay? So don't guess higher. What do you think? Any guesses? Yeah. 8 seconds? Okay, what do you think? Divide, okay, so you gotta do that for, that's a lot of math for me. What the heck? So what did that turn into? Okay, 5, okay, so you say 8, you say 5, what do you think? 1, what do you think? You think 6? I'm sorry, I couldn't hear you.
Yeah,
6. Any other guesses? 0.06. Any last guesses? You guys have to remember your guesses. You get 2 guesses. Did you guess already? You got 2 guesses. This is like the Price is Right with no rules. Okay, fine. We'll see now. Let's check it. It took 50 milliseconds. Okay. So actually, and for speed runs that fast, like it's good to run it more than once. Okay, now it took 40 milliseconds. So 40 to 50 milliseconds. So what did you guess again? Okay, so you're the closest. You're close with your revised guess, but you still didn't quite get it. And you don't get a third guess. Okay, so excellent. So why did I show you this? Complexity matters a lot if the number is big. So we went from 18.5 seconds to 40 milliseconds. So that is a speed up of, it's actually big enough that I have to think about it. So 10 times, 25 times, it's a speed up of like over 500 times. Okay, so it's huge. You can't compensate for using the wrong data structure by trying to fine-tune your code or buy a faster computer, etc. It's disastrous if you're working with large amounts of data. Working with a small amount of data, maybe it's not too bad. So one of the things you're going to do in this course, we're teaching the STL so you can rapidly change data structures and you can go through the menu of options. Milestone 1, that's what you're going to do, is actually choose the right data structures for the right function to learn how do you choose, what do you use for what. Okay, so you're essentially applying your complexity knowledge from 244. And it does matter a lot. Programs can be incredibly slow or very snappy based on whether you use the right kind of data structure or not. Okay, so let's take a break for maybe 5 minutes to like 4:16, so I don't keep you too long. Okay, let's get going again. So we're going to talk about a few more STL containers. Okay, so far you've learned about two STL containers, vector and list. Vector and list are sometimes called sequential containers. The reason called sequential containers is basically the order you put things into them is the order they come out in. Okay, there's a sequence, they maintain that sequence. There's another type of broad type of container called associative containers, where you don't put them in once in a sequence and expect to get them back out in that sequence. Instead, you want to look them up by a key, right? By essentially their contents. So I'm going to talk about what those are. You've already seen them in 244, so you know what these things are. We're just going to show you why you would use them and how you use them in the STL. There are two types of associated containers, one where it orders things and one where it does not order things. I'll show you both, and we'll talk about when you'd use one versus the other. Okay, so let's just start with motivating this new kinds of containers. So if I want to find some value in a vector, how do I do it? So I'm not talking about I want to get something from index 3. That's obvious. Just ask for index 3 with the square bracket operators, what vectors are great at. Let's say I put a bunch of strings in a vector. I got a vector with 1 million strings in it, they're all names. And I want to go find my daughter, Catherine. Okay, so I go look for Catherine in this vector of 1 million strings. I want to see which index is that. How do I do that? How would you write that code? So just knowing what you know now. Okay, so you write it using the 244 C++, you know, what would you do? And this is not that complicated. It doesn't sound that hard. It's not that hard. What would you do? So you write a for loop. There's nothing else you can do, right? So I got a vector with 1 million strings in it. I want to see, is this value, Catherine, exists in it? I have to loop through the whole thing, checking if everyone is equal to that string. So that's an order and operation. It's slow. Now in STL, if I don't want to write that for loop, I can actually have a templated function called find. So this is one of the functions that's in STL. Do it for me. But what it's actually doing is a for loop. Okay, so it's a little faster. It's the same thing. But I can call the find function. Find function takes 2 iterators to the range you want to search for. So if I want to search through the whole vector, I would say from the beginning to the end. And let's say the string I'm looking for is law. That's how I'd call find. And find will return an iterator. This is a standard thing for STL functions that sort of look things up, that find things. They return an iterator to it. What am I doing? Well, I've got some vector of strings, and I'm passing in the beginning, I'm passing in the end, and find will search through that with a for loop. And if it finds it, and it did, it will return an iterator pointing at it. Okay, so it works fine. Oops, let me get rid of that. But it's slow. It's order n. So if I want to do one lookup, it's fine. If I'm doing this a lot, and it's a bunch of loops, then this is going to be bad. It'll be slow. Okay, so we could do this a bit better, and you probably learned this in 244 or 105, like binary search. Does that ring a bell? Right. So we could sort this vector. And if we sort it, we can do binary search, which is logarithmic complexity, much faster. However, it's a pain, right? If you write all this code yourself to keep a vector sorted, every time you insert something, every time you erase something, you got to go in and change, make sure it's still sorted, okay? Which is both error prone, and that code could also get slow, depending on how cleverly you write it. So doable, but not fantastic. So it's better to actually just change your data structure. Right? It's a case where using a vector and then trying to keep it sorted is actually a bad solution. You're doing things in a not very efficient way, not a very productive way. So we should instead just change our data structure. So what data structure is inherently ordered? And you learned about it already, so I'm not asking a question where you have to guess. So it's a binary search tree, right? So you probably learned, well, I know you learned about binary search tree in 244, so there's no point in feigning ignorance, right? I know what's taught there. So a binary search tree. in the standard template library, the name for a binary search tree is a map. Okay, so you ask for an std : map, that means binary search tree. Okay, so what's good about using standard map instead of writing your own binary search tree? Well, it's templated, so you can just use it for any data type you want, rather than writing a whole bunch of different binary search trees for different types. It's probably better than the binary search tree that you would write yourself as well. So in ece244, you learned that a binary search tree, you insert things in it, you sort based on the values, deciding where to put it in, and you get this nice tree that doesn't have too many levels. And you can search it efficiently, because at every node, you decide, do I go down the left branch or the right branch? And you're kind of cutting how much stuff you have to look at by a factor of 2 every single level. So that's good. And you went through the code to write this, at least in lecture. You probably did not write what's called a guaranteed minimum level tree. Okay, so what I've shown here is called a balanced tree. It's the minimum number of levels. But if I inserted nodes in the binary search tree and it turned out that every node happened to have a bigger value than the previous one, I can get this. Okay, a highly unbalanced tree. This one is actually called a vine, because it turns out that it's always the right child that you would follow. This is slower, right? I have to do a comparison at every single level, and I have n levels instead of log n levels. So the binary search tree in the standard library will never do that. It will always have a structure that is either that or close to it. And they just write more complicated code. If the tree is getting unbalanced, what I'm showing over here, basically as you're inserting things into it or removing things from it, the class has complicated enough code that it detects it's becoming unbalanced, and it will actually perturb the tree to rebalance it. Okay? So it keeps it in this form so that it's not just that usually the insertions and deletions are log n and the find operations are log n, they're guaranteed to be log n. Which, did you guys learn about, did you write code to do self-balancing binary search trees in 244, or you wrote code and put it in where it seems the node should go? Do it on the blackboard. Okay, so you learned that you could do it, but you probably didn't write the code. So, and you could write the code, but it gets more complicated. So the STL does the more complicated code that keeps the tree either perfectly balanced or close to balanced, which gives you a better bounds on your speed. So, so you should use it. Now, standard map uses another STL class called pair. Remember, that was our example of a templated class that we wrote together in the first tutorial. Again, it's a useful class. It's a simple one, but it's useful. It combines a first element and a second element, and they can both be, whatever type you want, right, according to what you put in the template. Well, that's really useful for working with a binary search tree, because the nodes in a binary search tree fundamentally have a key and a value. So we use a pair to make that node, and then the binary search tree organizes the nodes. Okay, so I'm going to give you an example of a binary search tree. That's a realistic one. It's domain name lookup. So when you type a name into your internet browser, like Chrome, so you type something like google.ca, so google.com, so I just nationalized Google. So I guess it's google.com, because that's easy to remember. The internet does not work with strings. Okay? The internet works with integers called IP addresses. So that string has to be translated to a 32-bit, or some parts of the internet, 64-bit integer, which identifies what is the computer I'm trying to talk to. People don't want to memorize a bunch of random 32 or 64-bit integers. So we have what are called domain name servers. These are special computers at certain spots of the internet where they translate that string into the IP address and return it to you. And then your browser talks to that IP address for getting all the web traffic. You can imagine there can be a lot of traffic going into a domain name server, so you want it to be fast. It also can have a lot of strings, a lot of computers and domain names. So a binary search tree is a good option for this, because it's fast for lookups. And in this case, the key, the thing we want to use to look stuff up is a string, right? Google.com. And the value, the payload that comes back is an integer. So, for example, if I send in a key of this, one of the machines in the undergrad lab, I get back a 32-bit integer, which is its IP address, which we usually don't write as just a long 32-bit number. They're usually written 8 bits at a time with dots in between. So you'd actually see it written like that. But that is actually just a 32-bit number. You could actually just write the full one. Okay, so if I want to organize all of these strings and values, all of these IP addresses into a binary search tree, I need to I group them together first as a pair. Okay, so string and int, that's my key and value. Is everybody with me? Makes sense? Okay. So let's look at how we do this. And the code is pretty short. So it's too bad you guys don't write a binary search tree. You didn't write a binary search tree in the labs for 244, is that right? You used to. It's kind of a pain. You get lots of seg faults, lots of pointers and writing, which makes you truly appreciate how short this code is. But trust me, it's a lot easier than writing it yourself. Okay, so the first thing I do is I have to include the right header file. So for vectors, I include vector. For map, I include map. I need to declare my binary search tree. So its type is a templated class called map in the standard library. And binary search trees, maps, always take 2 types. Okay, the type of the key, which is a string for us, and the type of the value, which is an integer for us. So that's the type, and then I just give what is the variable name. Okay, I just made my binary search tree. The default constructor will make an empty one, so there's nothing in it. And now I start adding in entries, adding nodes in. And I'm going to do this in 3 ways, sort of using very explicit notation and then gradually getting shorter. All of them work. They're all the same, basically. So the first one, I'm going to make the data I want to insert very explicitly. So I say it's a pair of a string and an int, so key and value. And I'm going to call that variable Google. And the constructor is going to say, set it to google.com and this IP address. And now that I've got that pair, I can insert it in my binary search tree. So I use the name of the variable, DNS lookup. I call its member function insert, and I put in that pair. Okay? And insert is again a member function that exists for all the containers in the standard library. So remember erase, remember insert. You can use it with anything. Okay, so that was very explicit. I can shorten this a little bit. I can use the auto keyword to say make a variable called apple, and there's a templated function called make pair. So make pair just makes a pair variable out of the 2 things you pass. So here I pass a string and an integer. It'll make a pair out of that. Now I know the type of this, so I can use auto. And then I go and insert that. And if I want to be even a little bit shorter still, I could just not make any temporary variables, and I can just take toronto.ca, some IP address, make a pair out of that, and insert it in the binary search tree. Okay, so all those 3 things basically do the same thing. Okay, let's see. This is just telling me the same thing. Okay, so now I'm going to use a short syntax so I get more room on the slides. But hopefully it doesn't look mysterious. So again, I'm declaring my binary search tree. I'm sticking 3 key value pairs inside of it. And now I want to use it. So I want to do a lookup. So I'm going to use, well, I want to find something. Okay. So in the find command, it's a member function. You can use it on any, well, you can use it on a binary search tree for sure. I have to check whether I can use it on any container or not. And it's going to return an iterator. And I don't feel like writing in the whole long type of the iterator, so I'm just using the auto keyword. And this will work because I'm immediately assigning something to it, so the compiler figures it out. I need to pass something to find. So let's say I want to look up Google. What should I pass in? Should I pass in the key? Should I pass in the value? What makes sense? For a binary search tree, how should I find things? Pass the key or pass the value? You got a 50-50 shot. You've been thinking, I want to answer a question, but I'm too worried. Just take a shot now. But this is not that hard. What do you think? Yeah. Yeah, it's by key. That's what the whole thing is built for. You can't look things up by value in the binary search tree efficiently. So it's just like a vector. You walk it through the whole thing, looking at every single entry. So the whole point of a binary search tree is what you want to look it up by. That's what you make the key. So we're going to use the key, which in this case is our domain name. So we're going to ask, for example, for apple.com and for microsoft.com. Okay, so Apple's actually in the binary search tree because I put it in there. Microsoft isn't, because I didn't put it in there. So we need a way to tell, was it found or not? So what do you think? What do you think you can go look it up in the STL. It'll tell you what this iterator is set to if it's not found. But what value do you think it would use? So we need a special value for the iterator to mean I didn't find anything. If it's found, it'll have an iterator pointing to it, but it's also possible it's just not there. So it needs to return something in that case. If this was a pointer, we'd probably return the null pointer. And the null pointer would be like our special value that says it's not there. But it's not quite a pointer, right? Like it behaves like a pointer, but we can't just return null. What value could we return to mean it's not there? Yeah. Yeah, so we return end. End is like our special value that is like, it's both just past the end of the container, and it's also what we use as like our, it's not there. So that's exactly what it's going to return. So here, before I go and use this iterator, I should check that it's not equal to the end iterator. In this case, it isn't, because Apple was there. Now the iterator points at a whole node in the binary search tree, which is a key value pair. So if I want to print out the key and the value, I print out the first and the second elements of this pair to get the key and the value. Does that make sense to everybody? Okay, I'm going to take that as yes. Does everybody remember what this arrow notation means? What does that mean? So it's part of C++. What does that operator mean? Yeah, it means dereference, but through a function. It's like the dot operator. If you have data structure or a class, and you want to get it in sub-pieces, you use dot. If you have a pointer to a data structure or a class, you use the arrow. It's shorthand for dereference and use dot. Okay? The iterator behaves like a pointer. So if you want to get, this iterator points at a pair, and I want to get at the pieces of that class, which are called first and second, I use the arrow operator. Because it behaves like a pointer. Okay, so that's going to print out apple.com and a certain IP address. Okay, Microsoft wasn't here, so here I say if the iterator is equal to the end iterator, I'll print out not found. So this will actually print out not found. And I should check. If I actually didn't check and I just started writing code like this, it's like using a null pointer. Okay, you're gonna get an error of some type, right? Maybe a crash, maybe some other error, but it's not going to work. Common source of bugs, right? If it could return an invalid iterator, the end iterator, you should check for it. Okay, so we're going to iterate over a binary search tree. Now, what I just showed you is kind of the most common use of a binary search tree. You want find to be really fast, but maybe I also want to go through it and just print everything out. So this will be another little assignment. You're going to use iterators and a for loop to print out all the nodes in the standard map. Okay, so let's see, it's taking like 4 minutes, and go under exercise 2 in that same project, 208499 on codeboard.io, and yeah, try to write code to print out everything in the binary search tree. So it goes through the whole thing with iterators, print out the key value pairs. Okay, has everybody taken a crack at that, or as much of a crack as you want to take? Anyone want more time, or? Yeah, I would take that as people are either done or feeling pretty good about it. So let's look at the code for this. So yeah, the code's not that long. Okay, so I use the auto keyword here because the type of this iterator is a bit of a pain to write out. So I'm assigning the begin iterator to it, which means the compiler can figure out the type. So I can just use the auto keyword here. I'm going to start at the beginning. I'm going to go until I get to the end, but I won't look at the exact end. I'm going to increment each time. So that looks just like what I did for a vector. And that's part of the beauty of the STL, because it uses the same names for the member functions wherever it can. You kind of get used to writing with it. You can write lots of things that look similar for different containers. And then I print out the key and the value, right? I get an iterator to every node. I print out both parts. Okay, so let's see. Okay, so for a chocolate bar, what is this going to print out? We got to get it exactly right, because it's not that hard. So you take it. Okay, so you, I don't know. So go for it. Yeah. Oh, you just ran it too, so that actually helps. But that's fine. If you made it work, then that's useful. So it's Apple, Google. That's right. Okay, so when I put it in as Google, Apple, Toronto, you're saying it comes out Apple, Google, Toronto. Why? Yeah, it does it in order traversal. So remember, it's a sorting data structure. So that's why it's not a sequence container. Put it in this order, nobody cares if you put it in this order. It is internally sorting it. When you iterate through it, it actually is an in-order traversal, which you hopefully remember from 244. So it comes out in sorted order. So whenever you get a chance, feel free to grab one. Okay. So sometimes people ask me, well, how does this iterator work? This iterator seems a bit weirder. Again, the way you interact with it is just like basically the same way you were interacting with the vector one. You don't care, but it's good for computer engineers to know how things work. This is what's happening. Okay, so when you call the begin function, your iterator points at the node that has the smallest value, right? It's the left part of the binary search tree. And then every time you hit increment, remember, this iterator is a class. So it actually is walking through the binary search tree in order to update that iterator. So it'll actually go here after the first increment, there after the second increment, there after the third, fourth, fifth, and finally it'll hit the end and you'll break out of the loop. Okay, so it's kind of the power of iterators. Here you can see what it's doing when an increment is more complicated than just adding. It's actually walking through the tree. But that's fine, right? These are all templated classes. They can do whatever they want, whatever the STL decided to make them do. And it does the right thing. Okay, does that make sense to everybody? Yeah. If you wanted to, oh, if we go back to okay. So the type of this, okay, it's long. So the binary search tree that I showed here, just to make it short, I'm using an integer key, and I reversed it in this example. It's an integer key and a string value. So for the one I'm using, I would have to say std : map angle brackets int comma standard : string angle bracket close iterator. Does that make sense? Right. So I have to say what kind of iterator, and the kind of iterator is a map with a key of int and a value of string. So it's fine. I can type all that, but it feels like a pain. I either type that perfectly, in which case it compiles, or I get one character wrong in case it doesn't compile. So I just use all of them. Does that make sense? Okay, when you call the find function, so we're again looking up by key. So in the binary search tree here, the keys are integers. So let's say I look for the key of 2. I get an iterator that points at that value. Okay. Okay, so there are a few variations on map. So I'll just quickly walk through a couple of them. So let's say I've got a new binary search tree. So my binary search tree now is storing a string key and a floating point value, and we're going to call it, the object is called salary database. So salary database because I got a little startup, and I'm going to put my employees' names in as the keys and their salary in as the value. So I put my 4 employees in here, and notice that even though I'm a small company, I actually have 2 John Smiths. All right. So I want to go through and print out everybody's salary. I know how to write that, so I write my little iteration code to go through and print everybody out. And what's going to happen? Well, it's only going to print, well, actually, sorry, I didn't iterate over it. I didn't read my code carefully enough. I look up John Smith to print out what John Smith makes. Maps don't do duplicate keys. Okay, so the second John Smith does not go into the binary search tree. There's no error generated or anything. It just silently does not put them in there. If I do a find, I will get the answer for the first John Smith, because that's the only one that actually went in the binary search tree. Okay, so I'm overpaying my second John Smith. I couldn't store them both in the binary search tree. So you'd have to overpay him or have to fire him, have to force him to change his name. It's all very awkward. I don't want to do any of that. Okay, so sometimes you want to have duplicate keys, but the basic map does not allow it. Sometimes you don't want duplicate keys, in which case it's fine. So what do? So what you do when you hit something like this, you go, I want this, and the STL almost has it, but it's not doing exactly what I want. Just go look at the documentation. Documentation is big. So here are two of my favorite references. I'll just click on the c++reference.com. Okay, so let's go look at what it has. So it's a lot of documentation. And I told you that the part that's most important is the containers library. So I'm going to make this a little bigger so you can see it better. And I'm going to click on the containers library. Okay, so the containers library, it has vector, we already talked about that. It has list, we talked about forward list, it has a few other things that are not as important. And it has map. Okay, we've been using map, but it has a few things that are very similar to maps. And one of them is called multi-map. So that might sound interesting. So you click on multi-map, and it says, this is an associative container that contains a sorted list of key value pairs while permitting multiple entries with the same key. Okay, so it's a map, but this version of it allows you to have the same key put in multiple times. So that's actually what I want for my salary database. Doesn't make sense for me to say I can only have one employee with a certain name. Sound good? And this is, nobody remembers all this, right? So it's why you go to the documentation and you look to see what's going on and what are my options here. Okay, so now let's see what we do with this. So all I do, it's the same header file, and the documentation would tell me that. I basically just change the type of variable I asked for. Okay, instead of asking for a standard map, I now ask for a standard multi-map. I insert things the exact same way. I call this find function. Both of my John Smiths went into the binary search tree, but find only returns one node. Okay, so find is it's going to return one of these two John Smiths, and it's unclear which one. It's just going to return the first one that it finds. Okay, which is also not exactly what I want. So they're both in the database, but I don't have a convenient way to look both of them up. Yeah. Sorry, say it again. So because you have John Smith, yeah. Yeah. No, because they're not sorted on value. They're only sorted on key. So the order between the first John Smith and the second John Smith is arbitrary. You are right that they will actually be right beside each other in the binary search tree. Okay, because the two keys, that's the property of the binary search tree. It sorts. So it gives it something with two keys. The two keys have to be right beside each other in the tree, in the traversal order. But it's returning me one of them. So, what do I do? Okay, so I don't expect any of you to know the exact answer of what I do. Any ideas on what my next general step should be now? What's that? Yeah, you actually could do that. It would actually work, because you actually know that the next one, they all will be together, although maybe it's behind me. Maybe I didn't get the first one. Maybe I got the last one from find. You know what I mean? So now you're right. You know binary search trees, you can say, well, it's either going to be in front of me or behind me, or maybe I'm the middle one if there are a whole bunch of John Smiths. But you could write that code. You could say, hey, go iterate forward, go iterate backwards, find them all, put them all together. But this is also a relatively common problem. So before you write that code, what should you do? Check the documentation, right? Because yes, your knowledge of binary search trees is good. So you actually have come up with what you could do. Well, let's go read the documentation first to see maybe we don't have to do all this. It's like the mega blocks lesson again, right? So So you're doing a very good job of building with the little mega blocks. I'm gonna go see if there's a tree built big. So I'm gonna go down here and I look at, okay, I'm going to go to containers library again. And I'm looking at the multi-map. Okay, so I look at multi-map. I'm gonna zoom out one so you can see a bit more of this. Basically, it lists every member function that it has. Okay, so for every one of these containers, it lists all their member functions. And you'll notice that there's a whole bunch of them, right? So there's begin and end, there's size and so on. There's insert, there's erase, there's find. We've used all those. This one looks kind of interesting. Now, in practice, you'd have to read this a bit slower. Okay, like I know where I'm looking for. If I was actually just perusing the documentation, I have to go slower. But right after find, or very close to find, is this equal range. It says returns a range of elements matching a specific key. So I go click on that. That sounds promising. This stuff at the start is actually very hard to read. It's like the exact definition of the types and stuff. I generally don't start with that. What I do is I go look at, what does it say it's doing? And it basically says it's going to return a pair of iterators that are going to bound the range. So it's going to basically do what you were going to write code to do. It knows that they're all together in the binary search tree, but it's just going to give you iterators to the start of them and the end of them. And what's usually most helpful in this documentation is actually go to the example. Okay, the examples it's actually a general principle of teaching. The examples are generally much easier to understand than the general rules. So you go to the example, you look at it, and this is showing me a multi-map where they put in a bunch of values, and they actually put in the same key 3 times. And they're calling this equal range function with a key of 2. And you can see what they do. It returns what it calls a range, which is actually a pair. So pair is our friend, put 2 things together. The 2 things that is put together are 2 iterators. One is the beginning of the range, one is the end of the range, okay? And yeah, it is much easier to read this example than it is to puzzle through all of the detailed description before it. So read the high-level description, then look at the example, then maybe go back for details. Okay, so we do that. And based on that example code and reading the documentation carefully, I can figure out what to do. I shouldn't call find, I should call equal range. Equal range is going to return a pair of iterators. So I'm going to say I've got an iterator that's equal to the first, and I want to keep going until I get to the second, because they're like a begin and an end. And I want to go through and print out all the key value pairs. And that will now print out both of my nodes. This is what it's doing. If you look at the binary search tree, we've made a binary search tree that looks like this, right? So John Smith is kind of in the middle of the binary search tree. All of these equal range nodes must be together. That's a property of the binary search tree. So when we call this equal range, the range dot first, or range dash first, will point at the start. The range dash second points at the end. And STL always defines the end to be, this is too far, right? Stop. When you get to the end, don't look at it, stop, okay? So that's what you would get, and you can iterate through that range. Does it make sense? So in milestone 1, you're going to use a whole bunch of STL containers. You have to choose which one is which. You won't use equal range, but you are going to find that there are some functions that we just went nearby that are helpful. Okay, so that's why I'm showing you how to peruse the documentation. I mean, I'm not saying you can't use equal range. I'm saying you don't have to use it, but there are some functions in there that will be quite helpful to you that we didn't go over, but I hopefully showed you exactly how to go find them. Okay, that's it about map. Other containers. Okay, so we talked about map, we talked about multi-map. They're both binary search trees. They're log-in for insertion, log-in for erasure, and log-in for find. So they're fast. They're fast for putting things in, taking things out of, etc. Unordered map. Okay, so an unordered map, what is even faster than a binary search tree for looking things up? Hash table. So STL calls a hash table unordered map. Okay, so that's what an unordered map is. Unordered map is a little faster still. Order 1 for find, insert, and erase. A hash table has no order. So if you don't care about order and you need to do a lot of lookups by key, a hash table or unordered map is usually your best choice. If you do care about order, which you do sometimes, then a binary search tree or a map is usually your best choice. There's another variation on a binary search tree called a set. It works exactly the same way as a map. It's just sometimes you have a binary search tree where you have no values. Like the keys really are all you care about. In that case, you can use a set, which is a map with no values, only keys. The way you work with all of these things, the member functions you call, the way they work is the same. Okay, so that's why I'm not going through unordered map or set, etc. in any detail, because you basically write the same code, you just pick which data structure is the one you want. I'm not going to talk about these. There are other containers. Some of these will be useful in milestone 3. Not all of them, but you don't need them for a while. We're not going to talk about them. And let me make this go away. Okay, so let me quickly just contrast map and unordered map. So as I said, map is a binary search tree. It's log in to find things, and it's sorted. You can use it when the less than operator exists for the key. Okay, so to use a binary search tree in STL, you must have the less than operator defined for whatever type is the key. Okay, so less than is defined for integers, it's defined for strings, it works for all those things. If you make your own custom class, you have to have operator less than defined to use a binary search tree of it. Okay, an unordered map is a hash table, even faster for finds, order 1. It's not sorted. So if you need sorting, it's not a good choice. And in order to use it, you need to have a hash function defined for whatever your key is. You guys studied hash functions, I believe, in 244. Is that right? Okay, so I see some nodding, that's good. STL has already defined hash functions for things like keys, strings, so you just use an unordered map with those keys, it's fine. If you made your own class and you want to make an unordered map of it, you have to write a hash function. It's not that hard, but you have to write it, or it won't compile. It'll basically say, well, you're trying to use this templated class and it needs this, and you didn't make this. So you got to make it, or you got to use something else. Any questions on that? Okay. Okay, so standard template library is really big. We're not going to teach it all to you. We don't expect you to know it all. It is very useful. This is kind of the real way you do programming. You actually spend part of your time browsing documentation. So two of my favorite references, you should go to them when you're writing code to see, well, exactly how do I use this, exactly what exists. Also, you can find lots of examples online. You can ask on Piazza. Okay, so let me do a last demo, and then we're done for today. Okay, so what I'm showing here is a little example program that creates a binary search tree or a map. It has an integer key and an integer value, and I just called it map 0. I basically go through and I put 1 million random key value pairs into it, or arbitrary key value pairs into it. And then I go through and I do 10 million searches. So I randomly look up things by key 10 million times. So reasonably big binary search tree and a reasonably large number of lookups. Okay, so I should always build in release. Let's make sure this is the release build. If I want to time something, so I'm going to time this. All right, and it's fast. So here's my time. And that is 200 milliseconds, right? 0.2 seconds. So pretty fast, right? 1 million things, 10 million lookups, and it's only 200 milliseconds. Let's see. What do I do here? Okay, here is exactly the same code. Does puts 1 million things in now an unordered map. So a hash table. and then it does 10 million random lookups. So the only thing I've changed is don't declare a map, but declare an unordered map. Everything else works identically. You see, there's not much down here, right? So I basically just look it up, check if it's in was in the hash table or not. Don't do anything really useful with it. Okay, so this is now a map which is log n versus an unordered map which is order 1. The map took 200 milliseconds. How long do you think the unordered map's going to take? No reason you know this, but just take a guess. I have, okay. So I'm gonna resort to bribery. Whoever gets closest gets a chocolate bar. There are 4 chocolate bars left. Oh, what's that? You owe me a chocolate bar now. So, the question is, I got a binary search tree, and I got a hash table, map of unordered maps. The binary search tree took 200 milliseconds, and a million things in the table, in the tree, and I do 10 million lookups. I'm gonna do the same 10 million lookups in the hash table. How fast will it be? 200 milliseconds for the map. What do you think? Okay, so we're gonna go to the back. What do you think? 50. Okay, you're going with 50. What do you think? Any other takers? Oh, you're definitely gonna win there. Yes. What do you think? Yeah, what do you think? 6. What do you think? 20? 1. Okay, 6, 1, 13. Okay, you're just smart. You guys you're like, I'm just gonna kind of cut the thing. Can't change your vote. No, come on. No, no second vote. Okay, so let's see how fast it is. Took 90. Okay, so I think actually your first guess was very good. Right? I think you guessed. How did you guess? 50. 50 is actually closest. You're closest to 50. So I think everybody else guessed under you. Okay, so 50 is good. From 200 down to 50, all I changed was one word. The difference between log n and order 1 is not nearly as big as n and n squared, right? It was massive for n versus n squared. Log n is not that. But still, we got something that is, what did I say again? 90. So more than 2 times faster, and I only changed one word. So you might pass the speed test in this course, because milestone 1, you're going to find a bunch of speed tests. Where you use something like log n when you could use order 1, but you are giving yourself a penalty of a factor of 2, maybe more than 2 right off the bat. So in this case, unordered map is better, but not nearly as much better. Okay, so that's it for today. Thanks everybody. If I owe you a chocolate bar, go grab it.